Now, we have defined the area of a surface. The result is this. Suppose the surface has a parametrization, then the area is very simple. Okay. It seems very wonderful. No problem. Good. Unfortunately, we need to solve a problem because the area we define should be essential quantity associated with the surface. That is, it should be invariance. Once the surface is given, the area is determinant. The area is determinant. Okay, but as we know, given a surface, there are many parametrizations. So you use a particular parametrization R, computing this double integral, and define it to be the area. So if given another parametrization, that is phi from a region omega to R3. That is to say, we can also write, right? Then, if we compute the area using this new parametrization, we should have equal d eta. This is also a double integral over the two-dimensional region omega. So if you cannot prove that these two double integral coincide, the definition of the area surface we get is not well defined. Okay, so to define the area to be the integral, we need to prove that these two double integrals coincide. We will prove a more general result later. Now we go to some examples of computing the area of a surface. So before that, we have a look on a particular case, a special class of surface, that is graph of smooth functions, are very important. So we need to have a look on it. A particular case, in particular, if S is graph of a function g, say one function g, then what's the area of this surface? Then in this case, the parametrization can be taken as R xy to be xy gxy, right? So the partial derivative, I will already compute we already computed this result before, right? This is minus dxg minus dyg then 1. And the norm is square root of 1 plus gx squared plus gy squared. Therefore, the area in this special case is given by 1 plus gx squared plus gy squared. Okay, so this is the important special case of surface for a particular class of surface, graph of a smooth function. Now we consider an example. This example will further justify our definition. This is a definition. The next example will justify our definition of surface. Because we have defined the surface, we should apply our definition to some well-known surface. For example, the sphere. We know the surface of the sphere. Now we applied our definition to compute, using our new method to compute the area of the sphere. If the result is different from the well-known result, then there must be some problem in our definition. Okay, so let's check our definition by considering the sphere. So sphere is S2. S2 is the boundary of the unit ball in three-dimensional space. Okay, so for S2, we can take a parametrization. That is this map. The range of this map is 0 pi cross 0 2 pi to R3. The definition is given by sin theta, that is sin phi cosine theta, sin phi sin theta cosine phi. So the sphere is here, and given a point on the sphere, what is phi versus theta? This angle is phi. The point determined an angle between the z-axis is phi, and project this point into the xy plane. So this will give us another angle. Which the x-axis, this is theta. Okay. Now, using this parametrization of the sphere, we compute the area of the sphere, and the computation is a little tedious. Now, you can check that the derivative with respect to phi is the every component taking derivative with respect to phi. Therefore, the first component is cosine phi cosine theta. The second component is cosine phi sine theta. The third component is minus sine phi. And the derivative with respect to theta is minus sine phi sine theta. And sine phi cosine theta, then minus sine phi, and no, 0. The last component is 0. Then you can, using the computation, you can check that the cross product of these two vectors is the determinant of the first row is ijk, the unit coordinate vector, and the second rows is the r phi, that is cosine phi cosine theta, cosine phi sine theta, minus sine phi. And the third component is, therefore the first row is ijk. The third row is minus sine phi sine theta, sine phi cosine theta 0. So you expand this determinant according to the first row, you will get sine square phi cosine theta. This is the first component. The first component is the determinant of this block. Oh, sorry. This block. Therefore, since 0 is here, therefore only the multiplication of these two terms, which is a minus sign, but we already have a minus sign, therefore there is a positive sign. So this is the first component, the I component corresponding to the I coordinate vector. Okay. Similarly, you can compute the other component. The result is sine square phi sine theta. Then finally cosine phi sine phi. Sine phi, yes. Then the norm. Using the components of the cross product, you will see that the norm of R phi R theta is precisely sine phi. Therefore, the area we want to compute, the area of the sphere is the double integral over the domain of definition of the parametrization, that is 0 pi cos 0 to pi. Then R phi cos R theta d phi d theta. Because the norm of the cross product has already been computed, so we see that this is sine phi d theta. This can be written as 0 to 2 pi d theta, 0 to pi sine phi d phi. And this is 4 pi. The inner integral is 2, and the outer is the length of the interval is 2 pi. Therefore, this is 4 pi. The final result is 4 pi. Coincide with our well-known result of the area of the sphere. Therefore, our this example justified our definition of surface area. Okay, if our computation is different from 4 pi, then big problem. Okay. Now we consider a further example. S is the graph of a function. S is graph of this function over the domain D, the region D, x squared plus y squared less than 1. What's this? So x, y, z. This function, the graph of this function is a cone, unbounded above, a cone. But because x squared plus y squared is less than 1, so z is also less than 1. So the first surface S is the part of this cone bounded by the plane, cutting by the plane z equal to 1. So 1 is here. Using the plane z equal to 1 to cut this cone, the lower part of this cone, that is the part below the surface, the plane z equal to 1 of this, the part below the plane z equal to 1 of this cone is our S. Our S is here. The projection of this S, that is the domain of definition. This is our D. Okay, this is our picture. So how to compute the area of this surface. Because this surface is the graph of a function, we just mentioned how to compute such a area of such a surface here. So we need to take the derivative of the function, then applying this formula. Okay, so we compute the derivative. We see that derivative with respect to x is x squared plus y squared, and the derivative with respect to y is y x squared plus y squared. Now, the area is the integral, double integral over the domain of definition of the function, that is d. Then the function by our formula, the area is this integral. Now substituting the zx and zy into this integral, we will get square root of 1 plus x squared plus y squared. This is zx squared plus zy squared, then dx dy. So what's this? This is square root x squared plus y squared, that is 1 plus x squared plus y squared plus y squared x squared plus y squared dx dy. But this is square root of 2. So the result is square root of 2 multiplied the area of D. D is the unique disk without boundary. Therefore, the final result is square root of 2 multiplied the area of D, that is pi. So this is the area of this surface. Okay.